Now we are ready to perform this simulation for different advance ratios and blade pitch angles. First, from the Solution menu on the menu bar, select Clear Solution. This removes the solution while restoring the mesh to its state before initialization. Next, save the simulation with a new file name so that each operating condition can be identified easily. From the File menu, select Save As and save the file using an appropriate name. Set the desired advance ratio, then save the simulation. The simulation setup is now complete. Click Run to start the calculation. After the solution has converged, record the final values of the thrust coefficient and the power coefficient. Verify that the residuals have also converged, and examine the visualization scenes that were created during the setup. To simulate another blade pitch angle, first clear solution. Change the blade pitch angle parameter, set the desired advance ratio, and save the simulation using Save As. Regenerate the mesh. Save the file and then click Run. I have performed this propeller simulation using exactly the same setup for several operating conditions. I also digitized the experimental data for the 1600 RPM operating condition from the NASA benchmark report, and I have provided these data for you as well. The simulation results show very good agreement with the experimental data. In other words, we have successfully completed a solid validation study. The discrepancy between the experimental and the simulation results appears as an offset or an effective shift in the blade pitch angle. In some NASA reports, this variation in blade pitch angle has been attributed to structural deformation effects. You can now carry out the verification study on your own. Before concluding this chapter, I will briefly review the propeller performance equations so that you can use them in your own analyses. Finally, I will leave you with a few questions. Question 1. What is the practical effect of the rotating domain radius on the simulation results? Question 2. How do the dimensions of the stationary domain and its size relative to the wind tunnel influence the simulation results? Question 3. How does the choice of the side boundary condition affect the simulation results? Question 4. Using the blade tip Mach number reported in the benchmark, how can we determine the speed of sound or the ambient temperature? Question 5. If the blade airfoils had been wrapped onto a cylindrical surface during the propeller geometry generation, would the discrepancy between the experimental and the simulation results decrease or increase? Question 6. If an FSI simulation were performed, would the discrepancy between the experimental and the simulation results decrease or increase?